First of all, time is what you measure on a clock. And the earliest, the smallest measurable time is the Planck time, 10 to the minus 44 seconds. So all you can do is go back Planck time by Planck, step by step, in units of the Planck time, to the earliest possible moment, and that's the Planck time. It's not zero. And at the Planck time, there was no singularity. The singularity only occurs at time t equals 0. But you never reach t equals 0 because the whole assumption is that time is a continuous variable. That's built into general relativity. It's built into classical physics. But time is, in fact, discrete. It's discrete in units of the Planck time. We just don't notice that because Planck time is so small by our everyday standards. And theories that assume that time is continuous often run into quantum electrodynamics was a good example of this, where they assumed time was a continuous variable and ran into these infinities that they had to go into a lot of trouble to get rid of, but they wouldn't have been there if they had accepted the fact that time was discrete.
Okay, so the question is there were a couple questions in there. Is it possible that the multiverse has something to do with the singularity that is predicted by classical general relativity? And is there any possible evidence for or against from, for example, observations of the cosmic background radiation? So the honest answer to the first one is we don't know, of course. We need a quantum theory of gravity to describe what happens in the early universe, and we don't have one yet. It is very possible that a quantum theory of gravity, either string theory or something else, will help us understand how a universe like ours could have arisen either out of nothing or out of a pre-existing universe. So that's very possible, but right now we're in the we don't know stage.
Thanks, John.
Like, for example, there's hope that if we get better measurements of the cosmic background radiation, we'll not only be able to demonstrate that we live in an inflationary universe, but what kind of inflationary universe. If we can detect gravity waves, that'll help us constrain our models a little more. And I think realistically, within 5 or 10 years, we could be there and be able to answer these questions more definitively than we can today, and actually put to the test some of these speculations that we've been hearing about.
Last week, and in all the weeks before last week, I would go around giving popular talks about cosmology, and I would brag about the fact that we have experimental data, empirical information about what the universe was doing 1 second after the Big Bang. In a 14 billion year old universe, that's very, very impressive, 1 second after the Big Bang. As of Monday, I need to update all of my slides. We now have empirical information, real data, that tells us what the universe was doing 1 trillionth of a trillionth of a trillionth of a second after the Big Bang.
Now, the amazing thing is that we have learned, one of the great developments of 20th century physics, is that nothing is not so simple. When you put together the laws of quantum mechanics and relativity, then empty space becomes a dynamical thing, much more dynamical. When you put together quantum mechanics and special relativity, it turns out that there must be, that the empty space is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them.
Isn't it true that the casual agent that created space and time could simply be something else we haven't discovered yet? That is a simple chemical or quantum reaction that caused space and time, not a god.
Well, that's actually addressed by none other than Lawrence Krauss in his book, A Universe from Nothing, because he speculates that maybe some kind of quantum event brings the universe into existence.
Yes.
And I'll give you a short answer, but I got a 16-page review of his book on our website.
Great.
At reasons.org. Here's a short answer. Yes, you can get virtual particles popping into existence out of the quantum space-time foam of the universe, but they have to go back to the quantum space-time foam before the human observer can detect it. We call them virtual particles. And what Lawrence Krauss is saying, well, if we can do that with a virtual particle, why not the whole universe? But the greater the mass you try to bring into existence from the quantum space-time foam, the faster it must return. And the return time for something as big as the observable universe is 10 to the minus 120 seconds. And no matter how we interpret the days of creation, we all agree the universe is older than 10 to the minus 120 seconds.
Well, I couldn't have said it better myself.
And so this may be true, but if this is true, when a universe pops into existence, the laws of physics pop into existence along with it. And so you got no space, no time, no particles, no radiation, no laws. To me, that's a pretty good approximation of nothing.
My question points much simpler. How do you have dynamics without time?
That's a wonderful question. I wish I had the answer. But the point is, when people talk about, in fact, one of the arguments, look, I've just come from Australia where I was having this debate with a Christian apologist. And the argument given of cause and effect, that there had to be some purpose because there has to be, the cause and there has to be universal, the first mover, all the rest of the stuff. The point is, you're absolutely right. If time comes into existence at the same time as space, then the question of what happened before is not a good question.
It's not a scientific question.
It's not a scientific question. But I'm not sure it's not a scientific question. It's not a question we can answer yet because we don't have an understanding of that theory and how time can exist. I don't think you will agree with me that there's a vast difference between things we don't understand and things that are not understandable.
Oh, absolutely.
And so it's absolutely true that I can't, as a physicist now, adequately discuss what I mean by universes without time. But that doesn't mean that someday one of the young people sitting here won't.
No, but I'm just saying that's an obvious hole in the argument.
There's a what? That's a what?
That is, to me, the most obvious hole in the argument. I don't know how to talk about dynamics without time.
Well, you can imagine, you can. You can imagine, you can imagine a superspace, and I wasn't going to say superstring, argument where you have a Hamiltonian and things look like they're static, but locally they're dynamics when you take part of the system. You know how to do all that.
Yeah, but then you have a pre-existing space in which there are laws of physics.
Not space.
And you have
you don't have our
yeah,
space.
but you have a pre-existing entity of some
I don't
sort.
care if there's a pre-existing entity. Our universe did not exist. It came into existence.